All right, what if I told you there's a secret code? One that lets us measure pretty much anything. I'm talking about the height of a skyscraper or even the distance to a star millions of light years away. And believe it or not, this entire powerful code is built around just one simple shape. Today, we're going to crack it open.
I mean, really think about it for a second. How on earth do you measure something like a skyscraper or a huge mountain? What about that ship way out on the horizon? You can't just, pull out a giant measuring tape. So how's it actually done? It seems impossible, right? Well, I promise you, it's not. The answer, it turns out, is something called trigonometry. Now, don't let the name intimidate you. This isn't some crazy, complex mystery. It's actually a surprisingly elegant language, and it's all about understanding triangles. So today, let's learn the basics of that language together.
So, this entire code, with all its incredible power, it all comes down to one single shape, the right-angle triangle. I know you've seen this one before. It's the one with that perfect, square, 90-degree corner. This little shape, this is where all the magic happens. Okay, let's meet the players. First up, the main character in this whole story, the hypotenuse. It's always the longest side, that slanted one. And here's the important part. It's always opposite that 90-degree angle. Its position never, ever changes. You can think of it as the anchor of the triangle.
All right, now this is where things get really interesting, so pay close attention. The other two sides have names too, the perpendicular and the base. But, and this is a big but, their labels can change. It all depends on your point of view. See, if you're standing at angle A, one side is opposite you. But if you walk over to angle C, suddenly a completely different side is the opposite. Getting this idea that it's all about perspective is absolutely the key to the whole thing.
So how does this secret code actually work? Well, it's all about relationships. Specifically, it's about comparing the lengths of these three sides to each other. We call these comparisons ratios, and they make up the entire vocabulary of our new language. And the best part? There are only 6 of them. Just 6.
And here they are. This is it, the official code book. These 6 ratios are the heart and soul of trigonometry. Now, I know the names look a little weird, sine, cosine, tangent, but please don't let them freak you out. They're just names, they're labels. For example, sine is just a fancy way of saying, let's compare the side opposite our angle to the hypotenuse. That's all it is. Each one is just a recipe for a specific comparison.
Yep, that's it. Just 6. It feels way too simple to be this powerful, right? But I'm telling you, every single thing we do in trigonometry, all those incredible mind-bending calculations, they are all built on these 6 simple ideas. This is the whole foundation right here.
Okay, great. We've got the codebook. So how do we actually use it to measure stuff? Well, it boils down to a simple 3-step game plan that you can use every single time. 1. Figure out what you have and what you need. 2. Choose the right ratio from our codebook that connects those two things. And 3. Solve for the missing piece. Let's give it a shot.
All right, let's put this code to the test with a real-world problem. Picture this. You're standing on the street, exactly 100 feet away from a big building. You tilt your head up to look at the very top, and you measure that angle of elevation. It's exactly 45 degrees. So, the question is, with just those 2 bits of info, a distance and an angle, can we figure out how tall that building is?
Okay, let's break it down using our 3-step process. Step 1, identify. What do we have? Well, we've got our angle, which is 45 degrees, and we have the side next to that angle, the base, which is 100 feet. Now, what do we need? We need the height of the building, which is the side opposite our angle, the perpendicular. So, time to check our codebook. Which ratio connects the perpendicular and the base?
And if we look at our list, there it is, tangent. The tangent ratio is the perfect tool for this job. Why? Because its entire job is to connect the perpendicular side with the base side. It's exactly what we need.
All right, on to step 3, solve. We just plug in the numbers we know. Now here's a really cool little shortcut. For some common angles, mathematicians figured out the exact value of the ratio a long time ago. And it turns out the tangent of a 45-degree angle is always the number 1. Exactly. So our equation is super simple. 1 equals the height divided by 100. And just like that, the code gives us the answer. The building is 100 feet tall. Boom.
Okay, let's just pause for a second and appreciate what just happened. We just figured out the height of an entire building without even touching it. We never left the ground. We used an angle and one length to find a completely different length.
That right there is the magic of trigonometry.
And remember that magic number I mentioned, how tan of 45 is 1? Well, this is where that comes from. For a handful of really common angles, like 30, 45, and 60 degrees, these ratios always have the same predictable values. So this table is basically a cheat sheet. You can see it right there. For 45 degrees, the tangent is 1. Having these shortcuts makes the calculations incredibly fast and powerful.
So really, when you boil it all down, this is the superpower that trigonometry gives you. It's like a universal translator between angles and lengths. It's the bridge that lets you take something easy to measure, like an angle, and turn it into something that's impossible to measure directly, like the height of a building. And guess what? It works the other way around too.
And look, this is so much more than just a neat trick for math class. This secret code is literally running in the background of our world, all the time. It's the math that lets your phone's GPS figure out exactly where you are. It's what engineers use to build safe bridges and massive buildings. It's even how video game designers and movie animators create those incredible 3D worlds we love. It's everywhere.
So just think about that for a moment. The exact same ideas we just used to measure a building, you could use them to find the height of that tree in your backyard. And astronomers use them to measure the distance to galaxies. The principles are exactly the same. You now know the fundamental code that makes it all possible. So the only real question left is, what will you measure?